Hey, keep it down. I'm trying to record over here. Alright, welcome to video 15.4. Going to give you a quick little introduction to titrations, some techniques for performing them, and looking at pH curves. So titrations. A titration is a volumetric analysis that involves measuring the volume of a known concentration to neutralize a given volume of an unknown concentration. So in essence, we're looking at M1V1 equals M2V2, where the only thing you don't know is the concentration of your unknown substance. Okay. In acid-base chemistry, it really comes more down to moles of the acid component are equal to moles of the base component. That's really what it comes down to in acid-base titration. You either have an unknown concentration of acid and you titrate it with a base to see what its concentration is, or vice versa. You have an unknown concentration of base and you titrate with an acid to find the concentration of the other. You know you've got your titration completed when you reach a thing called the equivalence point. The equivalence point is the point where the titrant has reacted exactly. Go away. The equivalence point is the point where the titrant, that's your substance you titrate with, that's in the burette, when it has reached the equivalent, when it has exactly reacted with the analyte, that's when you've reached the equivalence point. Okay, so what's equivalent or equal at the equivalence point is the moles of your titrant and the moles of your analyte. So this first one's called strong, and the reason there's no other thing associated with this is because strong means you either have a strong acid, titrate with a strong base, or vice versa. You have a strong base, titrate with a strong acid. Either way, the titration calculations you'll be doing are very similar, as you'll see in the next video. So strong means the moles of the H plus are equal to the moles of hydroxide when you've reached the equivalence point. When you titrate a weak acid, in that case we call it HA, because weak acids don't ionize very well. They actually stay together mostly like this, whereas back over here strong acids do ionize completely and produce H+. So when weak acids are completely neutralized, the moles of your starting weak acid are equal to the moles of the strong base hydroxide you've added. And then lastly we have weak base, B, and when you titrate with a strong acid it turns it into BH+, but when your moles of H+ equal B, that's when you've reached the equivalence point. As you notice, there is no combination of weak because you never do a titration where your titrant is ever weak. The titrant is never weak, so the titrant is always the second thing in the list here. You never titrate the weak acid. I guess we'll look at that later why that is. When you reach the equivalence point, there's two ways to know you've reached it. One is to examine a pH curve, or sometimes called a titration curve, and what you're looking for is the inflection point. So the technical definition of inflection point, if I recall correctly from calculus, is when you change concavity, which means essentially it goes from being concave to being convex. Okay, so your curve is going this way, and then the curvature changes to the other side there. And that midpoint there, that's what we call the inflection point. And then whatever volume, and volume is measured on the x-axis of a titration curve, whichever volume that rapid increase takes place at, okay, it's the midpoint of the inflection of that vertical increase, or it's where you can see the concavity changing. That volume associated with it, that's the volume it takes to get to the equivalence point. And then there's also going to be an associated pH. pH is going to be on the y-axis. There's going to be an associated pH. And here's two titration curves. The first one here is a strong acid titrated by a strong base, and the second titration curve is a strong base being titrated with a strong acid. Okay, as you can see, they almost look like mirror images of each other, and we'll talk more about why that is later as well. The second way, I guess I am going to show you this in a bigger way. The second way to find the equivalence point is with indicators. Okay, this is called finding the endpoint. The endpoint is not the same as the equivalence point. The endpoint is when an indicator changes color due to the change in pH. So as you can see here in this little graph here, as phenolphthalein becomes more basic, and it's right around the pH around like 8.5ish, that's when it starts to turn that pink color. Well, we'll look at this in the next video, but when you reach the equivalence point for strong, it's always a pH 7. Well, the color change isn't going to occur until 8.5, but as you can see, the pH changes very rapidly in here. We're talking like one drop. One drop will take you from pH 7 to pH 8.5 very easily. And because of that, that's not a very big difference if you just add one drop. And that's why we say the endpoint is usually good enough to find the pH, or to find the equivalence point. But the endpoint is when the color changes with an indicator. The equivalence points are usually close to it, as long as you choose the right indicator. So not the equivalence point, but it's close if you choose the right indicator. Here is a list of some different indicators. We have methyl violet, thymol blue, methyl yellow, and so forth. Phenolphthalein is right here. It shows us the colors that those indicators take over a certain pH range. And after we're done really working with titration curves and doing the calculations with those, we'll end this chapter with looking at how you select the right indicator. And as you can see here, I mean, so like phenolphthalein doesn't turn pink until around 8.5, 8ish. Bromol blue is yellow when it's acidic, it's kind of green when it's neutral, and it turns blue when it's basic. So anyway, we'll investigate more indicators a little bit later. When you do a titration, the setup looks like this. We start off with a solution of known concentration. That's the solution inside the burette. So the titrant, we know its concentration. So I'll call that M1. Okay. Then we are using a burette, and a burette is the precise apparatus to deliver the titrant. You always have to make sure you measure an initial volume. You also have to make sure to measure a final volume, and I kind of wrote this backwards. Subtract the initial from the final to find out how much volume you've actually added. Okay, that's really important. Don't ever forget to get the initial volume, because if you do, you'll end up with a final volume, and it means absolutely nothing. So always make sure you have that. On the burette, there is the valve right here, and sometimes that can be really sticky in terms of like how hard we have it tightened. And if you really have a hard time turning this, you can loosen up a little bit, but you gotta be careful because you can form leaks if you loosen up too much. So that's the valve. Allows us to adjust it different rates. The container at the bottom here is called an Erlenmeyer flask. Remember, we use this because that the shape of the container allows you to swirl it and not allow it to slosh out of there for spilling. And also, when drops come in here, they kind of splash, and that also helps make sure it stays in the solution, or stay in the solution inside your container. And then lastly, we have the analyte. The analyte is the solution down here, and that's going to be M2. It has some concentration that we don't know of, and we're trying to find it. Okay, so that's called the analyte. And then typically with both of these, when you're all done with your titration, you're going to solve for V1, which is how much you've added overall to reach the equivalent point. And then you do know, like when you pour this analyte into here, you know what volume you used of it, so that's V2. And essentially what we're always looking for is, what's that concentration of this analyte? We're trying to analyze that substance and calculate its concentration. Okay, lastly, we have some important techniques for titrations. Make sure the burette tip is always full of titrant and there's no air bubbles. When you first put your burette together, typically we have them set up for you. This area right here will initially have air in there, so you have to make sure you open the valve and fill it up with titrant here. And sometimes air gets trapped in there still, so make sure you open up all the way wide and collect some stuff in a waste beaker down here, not a Erlenmeyer flask, and make sure you get all the air out of there to alleviate any problems you might have with that. Also check for leaks and make sure that valve is tightened. You want it tight, but not so tight you can't turn the valve. If it's too loose, things will leak around it. Make sure you check the place values on your burette. You need to know what these markings are on the side of your burette here, because that helps you figure out how many sig figs of values that we know for sure. Okay. Also, it's really useful if you put a white piece of paper underneath your Erlenmeyer flask. Helps you notice the color change better. And then lastly, I think this is a really important one. Make sure you know which way to turn your valve. You guys have all been there. I've seen some of you perform this already. Your the person who's in charge of the valve is getting a little freaked out by the color changing down here, and they're trying to get one drop, and then all of a sudden they're really close to that one drop turning to colors, and what they'll do is they'll open it up by accident. Always make sure you know which way you're going to turn it, so that way it speeds up or slows down as you want it to. Okay? So this is a little introduction to titrations. In the next video, and for the homework on that next video, you'll be actually doing the calculations to calculate pH changes for titrations.